Storage is one of the main culprits of performance issues for many systems, from laptops and desktops to standalone servers, and virtual environments are no exception whatsoever. Therefore, a good solid understanding of storage basics is crucial to maintaining your virtualized environments. I expect you'll already be familiar with most of what I'm about to cover. It is as relevant to physical servers as it is to virtual environments, but I want to make sure we are all on the same page. So we are going to start off by discussing RAID, Redundant Array of Inexpensive Disks. RAID allows us to combine multiple disks into a single logical disk. This allows for improved performance and usually resiliency, so that the failure of a disk does not cause an outage. How it does this depends on the RAID level that you've selected. Let's start with RAID 0. This offers zero redundancy. The data is written in stripes across both disks, and the capacity and performance of both disks is combined as a virtual disk. But if one of the disks in the set fails, then the virtual disk will go offline, and the chances of recovering the data are extremely slim. Imagine trying to restore a document in a foreign language when you only have every other letter. We can read and write to both disks simultaneously, so this provides the best performance, but with no redundancy. Each block only has to be written once, so it is considered to have a write penalty of 1. We'll talk more about the write penalty later. It's rare you'll see RAID 0 used on a real-world platform. It has its uses, for example, for cache disks, where the application can continue if the cache disk is lost, but that's about it. Next we'll talk about RAID 1, also known as mirroring. This is the simplest form of redundancy for disks. Each block is written simultaneously to each disk. Sometimes people think of the data as being written to one disk and then duplicated to the other, but this is not the case. Both copies of the data are written in parallel. The write is not considered complete until both copies have been written. If one of the disks fails, the virtual disk remains online. When the failed disk is replaced, the data is copied from the first disk to restore redundancy. As each block must be written twice, RAID 1 is considered to have a write penalty of 2. We can also only use the capacity of one of the disks. Next we'll look at RAID 5. This is also known as distributed parity. Like RAID 0, the data is striped across all but one of the disks. But then RAID 5 uses an algorithm to generate a parity block which is written to the other disk. A common misconception is that one of the disks contains the parity for all of the data, but this is where the term distributed parity comes in. The parity for the next stripe is written to a different disk. This continues for each stripe. In the event that the disk fails, RAID 5 uses the parity data to reassemble the missing pieces on the fly. The virtual disk remains online, but performance can be badly degraded as the RAID 5 array reassembles the blocks as they are read. When the disk is replaced, the data, including the parity blocks, is rebuilt onto the new disk. RAID 5 can only ever tolerate one disk failure. Each block is only written to once, but we also need to calculate and then write the parity data. As such, RAID 5 is considered to have a write penalty of 4. RAID 5 is more space efficient than RAID 1. Out of the 3 disks we can use the capacity of 2 disks, but this is at the cost of a greater performance impact. Finally, there is RAID 6, often referred to as double parity. This is very similar to RAID 5. Each block is split across all but 2 of the disks. and 2 separate parity blocks are written, again distributed across the disk. This configuration can survive the loss of 2 disks. We write each block once, but we need to calculate and write 2 parity blocks. Therefore, RAID 6 is considered to have a write penalty of 6. So let's look at how we use the write penalties to select the disks for our server. The most important metric for storage performance is IOPS, the number of I/O operations per second generated by the VM. You can use perfmon to measure the IOPS on an existing Windows server. If you are deploying a VM for a new application, you can ask the application vendor how many IOPS they expect their app to generate. Let's say that you determine your VM will generate 140 IOPS. Next, you need to calculate how many of these IOPS are reads and how many are writes. You may have this information already from either the application vendor or from scoping it out from an existing server, but 80% read and 20% write is a good guideline. We leave the read IOPS as they are because under normal circumstances, RAID does not have an impact on read performance. We then multiply the write IOPS by the write penalty. So for RAID 0, we multiply by 1, which of course has no impact. For RAID 1, we multiply the writes by 2. For RAID 5, we multiply the writes by 4. And for RAID 6, we multiply the writes by 6. Again, this is all linking back to that write penalty that I mentioned. Now we know how many IOPS we expect the VM to generate on each RAID level, we need to decide which disks to use. To do this, we need to understand how many IOPS each disk can process. 7,200 RPM disks can handle 80 IOPS. 10K disks can handle 130 IOPS. 15K disks can handle 180 IOPS. SSDs can handle well over 1,000 IOPS, and the newest NVMe SSDs can handle in excess of 100,000 IOPS. These are typical values. There will naturally be variances depending on a variety of factors, and these figures are based on random IOPS, where the data is scattered in various parts of the hard drive and the disk is having to move backward and forward to read the relevant blocks. Sequential operations, where the data is all in the same place on the disk, will be a lot higher. This is why copying one large file is often faster than copying lots of small files of a similar size. If we decide to use RAID 0, we need 140 IOPS, so we can achieve this with 2 7,200 RPM disks. If we want to use RAID 1, we need 168 IOPS. Our 7,200 RPM disks won't quite be fast enough, so we'd be better moving to 10K disks. If we choose RAID 5, we need 252 IOPS. We'll be using 3 disks, so our 10K disks will still be fast enough. If we use RAID 6, we need 308 IOPS. We will be using 4 disks, so again our 10K disks will still be suitable. This is a simple example, but this should help you to right size your disks from day one. If you suspect you have an issue with disk performance, the first place to look is the disk queues in the VM. This performance counter represents the number of operations queued up. In a Windows VM, anything above 2 is likely to indicate an issue with disk performance. This value is scaled to the thousands, so a value of 2 means 2,000 queued requests.